Hello friends, I am Hemant Kumar Naik and I am uh, speaking to you in front of camera, right? So as I usually do, right? So now I will share my screen to you, right? So that you can see. I have shared my screen to you, right? You can see. Let's start some PowerPoint. Today I will study about. Today I will talk about biomass conversion, right? So for that, I'm opening my PowerPoint. Right? I have prepared one slide uh, related to biomass conversion. This is so I have shared the PowerPoint presentation. Okay, so I will be talking about subcritical hydrothermal liquefaction of cattle manure to bio. Right, so we have biomass sample as cattle manure, and we want to convert cattle manure to bio oil, right? So and the effect of conversion parameters on bio oil yield. So basically, we will looking about the bio oil yield, and when you produce bio oil, then we also characterize bio oil. So this is Evan Kumanak, and I am working under Dr. Sushil Kumar, Department of Chemical Engineering, IIT. So actually, I have taken one reference, rather say research paper, and I have done literature reviews on different papers related to my topic. So I find extract as cattle manure was converted to bio oil, right, by subcritical hydrothermal liquefaction and uh, in presence of NaOH. NaOH they are taking as a base. So they are using base. Right? So this is the thing. And after that, effect of conversion temperature. So what different temperature they have done reaction, and they have used process gas and pressure also in initial how much initial pressure is required. They are studied this thing also, and time reaction time, residence time, and mass ratio of cattle manure to water. This is important, how much water we are taking to make slurry. This is important, right? So we have to go like that, and then bio yield was calculated, and the bio oil was characterized in terms of elemental composition, how much means how uh, carbon percent, how hydrogen percent, how much is there. So and then heating value also, and after that ultraviolet visible spectroscopy, yes, and FTIR, that is Fourier transform infrared spectroscopy, as gas chromatography and gas chromatography mass spectroscopy GCMS. So the bio oil yield dependent on the conversion temperature and the process gas. Higher initial conversion pressure, longer residence time, and larger mass ratio of kettle manure to water are had negative impact on the bio oil yield. So the positive and negative impact will be there. So they have studied all this, and they are getting the higher heating value of 35.53 megajoule per kilogram, right, on average. The major non-polar components of bio oil were toluene. Non-polar, what non-polar component present in the oil, they they know from GCMS analysis, and they are getting toluene, ethyl benzene, and xylene as the non-polar uh, component, which are component of crude oil, gasoline, and diesel, right? So the diesel also some non-polar component will be there. So they are basically comparing with the bio oil. Right, so this is the thing. And next is some introduction. So we want to study about liquefaction of biomass. So what the typical this picture shows typical liquefaction setup. Right. So first, right. So I am taking cattle manure or cow dung as my biomass source. So so cattle manure has in the past been considered a cheap fertilizer, right? So this is one of the initially it is used for fertilizer, but due to the intensification of livestock practice, it is now considered a waste product. There are so many in livestock, right? So now it is a waste product, right? So, causing environmental pollution also. So we have subcritical hydrothermal liquefaction. Basically, hydrothermal liquefaction means water plus heat, right? So, and subcritical means below critical point. Below critical, so this is the thing. And is a potential technology for the conversion of cattle manure to bio-oil. Right? So this is the important technology. And since bio-oil combustion emissions are biogenic in nature, they may contribute less to greenhouse gas emission than fossil fuel. Right? So this is the thing. Our fossil fuels are basically the producing greenhouse gases, but if you use bio-oil, so less pollution will be there. So this is the introduction of using uh, cow dung and converting bio oil. Right? So there are so many literature. So right, so like biomass, they are taking pine wood, and temperature is around 280. Right? Pressure they have used nitrogen ambient condition, and residence time was 15 minutes, and yield they are getting is 23 to 33. Yes, these different biomasses samples were there, and one is dry and one is wet. So for wet, they are converting based on volatile content, how much volatile content is there, and how much oil is produced. So divided by volatile content, they are getting bio oil yield conversion, right? So this is for wet component, we have to use this and. Uh, Uh, nice. And I uh, cursor like the laser pointer. I was selecting laser pointer, but it is not working. And these are typical biomass sample, right? Sewage waste is there, domestic garbage, algae, fine manure. So they are getting different bio yield, right? So next is literature review. So what are the previous work related to my topic? So this is basically literature review. Right. So first, each Kumar et al. 2014. Pine I would do taken by biomass sample is pine wood, and temperature is around 320 to 350 degrees Celsius. Residence time they are taking greater than 200 seconds, and water they are using 10 weight percent. Right, so reactor is basically autoclave. So what they are getting, formation of undesired vacuum residue is not due to the secondary condensation of the bio but rather to the incomplete primary depolymerization of the biomass with the simultaneous dehydration of fragment. And next is the resulting fraction of vacuum residue 30% is still too high to allow effective recycling of the bioalgae liquefaction medium. And so this is their work. And after that, Kumar Lange was Van Rossum et al. 2015 taken by pine wood as biomass source, and conditions are 320 degrees Celsius, 400 residence time. Yes, with 9 ml volume is there. Feed is like curl wood and water, 60, 20, 20, 20. Acid and base additive, they have used acid and base additive also, and the reactor was just same, means autoclave. And they are getting high liquid yield as 90 carbon percent and single run. Use of base lowers the yield of vacuum residue, while acid increases it, right? So base, if you use base, then yield is decrease, and if you use acid, it increases. Right? The higher rate pH, higher the pH, the lower the vacuum residue. So if the pH is high, then vacuum residue will be lower. Right? So the addition of base also catalyzes the degradation of the solvent, right? And the consecutive degradation of the bile upon bile recycling. There are many more literature review also. So after studying literature review, I find research gap. So like the upgrading processes of hydrothermal liquid bio-oil to alkene hydrocarbons are required before it can be directly used as a liquid transportation fuel. So if you want to use bio-oil as a transportation fuel, then you have to break the right. Need of intermediate stabilization step and separation of the solvent from the whole bio-oil before using it as a liquid solvent. So separation is needed, right? Like purification, you have to. So and after that, alternative approaches are needed, such as applying catalyst, and are removing or cracking the vacuum residue prior to recycling. And limited studies are found for liquefaction of cow dung in the literature. So, yeah, this is also the thing. Cow dung, limited literature are there. Means less studies on related to cow dung in the literature. Yes, these are the research gap. And after that, once I read this paper, then coming to methods, how they are doing the reactions. So for that, reaction for the subcritical hydrothermal liquefaction, kettle manure was carried out in a 1.8 liter stainless steel reactor. Right, so this is par reactor. So its capacity is 1.8 liter. So for that, we have to do 500 ml of kettle manure slurry with zero point 0.5 mole of NaOH, right? So NaOH they are getting and was placed in the 1.8 liter reactor. The remaining 1.3 liter head spread was purged with the process gas, right? So this is the and after all the setup, I mean closing of the gas inlet, the reactor was heated to the set point temperature at a rate of approximately 2.7 degrees Celsius per minute. After certain residence time at the preset temperature, the reactor was cooled at a rate of 13 degrees Celsius per minute to 100 degrees Celsius. Okay, so the basically what temperature we want to do the reaction, we have to set, and after that, when temperature reach, we have to wait for ration time, right? 30-minute ration time, so we have to wait for 30 minutes, and after that, we stop uh, furnace, right? So and we collect the liquid product and gas product and then analysis. So, what the typical composition of cow dung is that elemental analysis shows carbon is 35.38%, right? And hydrogen is 4.73%. Similarly, and volatile content is about 16.29%. So these are main thing which you want to look at, right? So this is basically ultimate analysis of cow dung. Right. And this are the purification method. As once we done reaction, then we have to separate liquid into bio oil, right? So for that, separation of bio oil from aqueous product is there. So first solid residues in the aqueous product were removed by using filter paper, right? So by filter paper, first we want to separate the particulate matter. So we with filter paper, and then the liquid product was extracted by uh, CH2 Cl2 with the volume ratio of 1:1. How much amount is there? We have to use same amount of solvent. And so here in this case, CH2 Cl2 was used as solvent and separation product due to separation process. So layers, different layer will be appear, right? So and CH2 Cl2 extract was then treated in a rotary evaporator. Whatever extract we are getting after solvent extraction, then we have to evaporate in a evaporator, right? So and so that remove CH2Cl. So you have to remove solvent. So in this case, CH2Cl2 at 40 degrees Celsius, CH2Cl2 will be a rise because its boiling point is 40 degrees Celsius. The remaining liquid was considered bio oil in this situation. Right? So whatever liquid remains, this is the basically bio oil. Right? So bio oil yield, how you can calculate? So for that, we have formula bio oil in percentage, weight of bio oil divided by volatile content into 100. So where WBO is the mass of bio oil in gram, VC is the volatile content gram of input kettle manure before conversion, right? So in high rating value, kilojoule per kg. High rating value is calculated. Its formula will be there 3.55 C square minus 232 C minus 2230 H plus 51.2 the carbon into hydrogen plus 131 nitrogen plus 20,600. Here HHV is the high rating value and the CHN or mass percentage of the carbon, hydrogen and nitrogen in the bio respectively. So this is the formula from which we can calculate the bio yield. Right. So and separation of bio from aqueous product which are already studied, means already talked, right, guys? And then next we will discuss some results and discussions. So this picture shows bioavailable yield versus temperature. The first one, and the second one is bioavailable yield versus initial pressure of process gases in PSI. So we can see here different process gas were used: CO, H2, N2 air, and y-axis shows bioavailable weight percentage of volatile content. And the x-axis shows temperature, different temperature they are using 250 to 360. So basically, effect of conversion temperature on bioavailable with the CO, H2, N2, and air as a process gas. Conditions are 500 ml of kettle manure slurry with manure water mass ratio of 0.25, 0.5 mole uh, of NOH is used. Residence time was 15 minutes. Zero PSI initial pressure of process gas. So zero PSI, they are using zero PSI. And they are getting this. You can see higher bioavailability in case of CO gas. If you use CO gas, then we can get higher bioavailability. Right? So this is the thing, and this picture shows the effect of initial conversion pressure. Right? The initial conversion pressure. So basically, in at around 310 bioavailability maximum, and here initial process gas PSI. So 0, 20, 40, 60, 80, 100. So bioalid nitrogen, and this one is for residual solid nitrogen. And triangle one is for residual solid CO. Triangle and solid triangle, and this simple triangle is bioalid for CO. So yield of bioalid under residual solid versus initial process pressure of process gas price. So this is the result discussion part, and they are using different residence time versus bioavailable yield. Right? So this is the different, and mass ratio of kettle manure to water. This is important parameter. How much water you are using is important, right? So this is the picture for this, and what characterization is characterization elemental analysis, right? CHNS analysis, and heating value you have to consider, ultraviolet visible to know conjugate structures. FTIR, there are different compound present in the sample. So for that, different bend is there. From that, we identified functional group of the bioavailable, right? So in the GC and GCMS, GC and GCMS, test chromatography and gas chromatography, mass spectroscopy. Right. So in this, we analyze gas sample, and GCMS we analyze liquid sample. So GC, based on whatever gas present, we identify concentration of the different component. Right. And GCMS, we know the non-polar and polar compound present in the liquid oil. So same to know morphology, and the structure of the inside of the sample. We want to know char morphology. So for that, same still electron microscope is there, and particle size, transmission electron microscope, and thermochrometric analysis. So when decomposition takes place, to know the boiling, to how the recent temperature. We want to know when moisture remove, when volatile content removes. So the decomposition of the content, whatever sample is there, we want to know decomposition temperature. So for that, we do thermochrometric analysis as well. Right? So these are the characterization which is used to know the biological characteristics. So characterization of bioavailable source, here there are different kettle manure there, hydrothermal bioavailable there, bioethanol, biodiesel, pyrolysis bioavailable, gasoline, right? So there are different. So you can compare this, like this for kettle manure, carbon is around 35.38, and right, so you can see bio-oil, hydrothermal liquefaction, bio-oil, carbon percentage around 73.72, bioethanol is 52, right? So you can see. I think, high heating value is megajoule per kg. So maximum heating value is for gasoline, right? And bio-oil is around 35.53. So this is thing. And gas chromatographic analysis of bio-oil, gasoline, and diesel. So this is relative abundance percentage versus retention time. So bioil from hydrothermal liquefaction kettle manure. So this is the typical different for gasoline, diesel, and bioil. Right. So you can see the GCMS analysis. So the conclusion after that, we come to conclusion that cattle manure was converted to bio oil by subcritical hydrothermal liquefaction, that is HTL. So this is the maximum bio oil yield is around 48.78% at around 310 degrees Celsius with CO as the process gas. Yes, a residence time of 15 minutes, and the cattle manure to water mass ratio is around 0.25. So 0.25 there, and 15-minute reaction time, and they are getting bio oil yield as 48.78% at around 310 degrees Celsius. Right, so this is the thing, and after that, bio oil yield from HTL of cattle manure dependent significantly on the conversion temperature. Right, conversion temperature and process gas play important role in the bio oil production. Right. So, and then higher initial conversion pressure, longer residence time, and the larger mass ratio of cattle manure to water, however, had negative impact on bio yield because bio oil was converted to gases and the char are turned under these conditions. Right. So, HDL bio oil was characterized using different characteristic techniques based on the elemental analysis. The higher heating value of bio oil was 35.53 megajoule per kg on average. The ultraviolet visible spectrum showed the bioil had conjugate structures. The FTIR analysis indicated that the bioil contained functional group of polyalcohols, carboxylic acid, phenol derivative, and alpha, beta unsaturated ketone. Okay, so these are the FTIR analysis. From that, we identify the given bioil has these functional groups, right? So this is the inference. And after that, GC and GCMS analysis showed that the bioil did not contain C4, C15 alkanes, the major component of gasoline and diesel. So, right, gasoline and diesel I have C4 to 15 alkanes, but the our bioil has not this. So no major non-polar component were toluene. That's its major non-polar component are there. So from GCMS we identified non-polar component also. So they are toluene, ethyl benzene, xylene, which belong to crude oil and are aromatic compound of component of gasoline and diesel. So this is the thing. So in bio-oil, we know that toluene, ethyl benzene, and xylene is present from GCMS analysis. So is also present in gasoline diesel. So if we blend some amount of bio into diesel, then we can use as a transportation fuel, right? So these are the conclusion, right, guys? So if you do liquefaction, then these are the results of cattle manure. All right. Thank you for your attention. I'm stop my share. And, this is thing. So thank you guys. Have a nice day being here. Good have bye bye. Right? Good night. I'm stopping here.